Well, even if you throw an object upwards, it will accelerate upwards.
Yeah, I know. Yeah.
Until it slows down.
Yeah.
So, you can't have it both ways.
But when you throw an object upwards, it's acting against its own mass.
When you throw a ball up in the air, it's accelerating upward. It's acting against its own mass. Please tell me you two didn't just say that. Well, hello everybody. Welcome to Blue Marble Science. Peter and Pete claim they're exploring scientific claims and exposing reality. I'll tell you what we'll do today. We'll explore Peter and Pete and expose what they're doing. Now, these two guys deny gravity. They claim it doesn't exist, and they claim the only reason a Cavendish torsion balance moves is because of heat differential. This is going to be fun.
We got a comment on the video. We got a comment.
I don't need this.
I don't need this. I don't need this, man.
Yeah, it was a Globie.
He's a Globie. He's a fucked up individual. Of course, he's got mental health problems. Anyway, but with regards to the Cavendish experiment, he writes, or she writes, you acknowledge that the results see an attractive force between any types of masses. Therefore, don't you think it's too big a coincidence that if you throw an object up in the air, it always accelerates towards the huge mass below it, the Earth, given that you don't think it proves a gravitational force? Well, even if you throw an object upwards, it will accelerate upwards.
Yeah, I know. Yeah.
Until it slows down.
Yeah.
So, you can't have it both ways.
But when you throw an object upwards, it's acting against its own mass.
When you throw an object upward, from the instant it leaves your hand, it is accelerating downward at a rate of 9.81 meters per second squared. It's acting against its own mass? That's just word salad. I have no idea what that even means.
Absolutely, of course, yeah. But anyway, now, agreeing there exists an attraction between masses does not prove its gravitational attraction at all. That's just a hypothesis. Cavendish recognised in his paper that a heat differential caused the attraction.
Your concept that heat or temperature somehow or the other can be the direct cause of the torsion balance moving fails immediately, and this is why. For the torsion balance to move, you have to apply a force to it. Neither heat nor temperature are forces. Now, you're using heat and temperature interchangeably, and technically that's really not right. Let me explain it to you. Heat is the amount of thermal energy that is transferred from a hotter system to a colder system if they're in contact with each other. Temperature, on the other hand, is simply a measure of the average kinetic energy of the atoms or molecules in a system. If two or more objects are at the same temperature, they're said to be in thermal equilibrium. And objects in thermal equilibrium at the same temperature do not transfer any heat. As we'll see later, a temperature differential can cause some circulating air currents that impart a force on the balance and cause it to move, but that is a transient condition we'll get into in more detail.
So on one hand, there's a heat differential, causes objects to laterally move towards each other, or there's this insane idea that gravity is the cause. However, the idea of gravity attempts to explain falling objects, not lateral motion.
Hold on there, numpty. Newtonian gravity describes the apparent attraction between masses. You've seen this formula at least 100 times. The apparent force of attraction is big G times the product of the masses divided by the square of the distance between their centers. Falling is a good example. That is why your dumbass is attracted to the Earth.
It's likely that a heat differential is the cause for lateral motion observed in the Cavendish experiment. That's our view.
Yeah.
And I still think we hold.
Yeah,
we'll hold that.
Yeah, you come on our channel every now and again to defend your shit science. You got mental health problems.
Of course. So James Smith also, well, where are they coming out from? They're coming out of coffins.
He says, have you read Cavendish's own report?
Yeah, now let's...
Yeah, hold on. No. So we put, yes, that's where we got the information from. Cavendish also used the mass of water as a constant when calculating the mass of the Earth. And we all know the Earth isn't entirely made of water.
Cavendish related the density of Earth to the density of water. It's what we call specific gravity. I suppose he could have related the density of Earth to the density of petunias if he had wanted to, but that doesn't make a lot of sense. Just use water. That's what we always use.
Absolutely.
So I don't need this, says.
I'd like to see what Cavendish said about the temperature difference. I think there's a bit more context to this. I mean, it is quite a bold claim to say that for all the thousands of times this experiment has been carried out, every single time, one weight has happened to be warmer than the other, resulting in an attractive force, even though that's not the overall conclusion of the experiment. But one thing I would like to say, and that is, you'll always find one object is bigger than the other.
Absolutely, always.
The one object is always bigger than the other.
And if one object is bigger than the other, it's going to have a different heat signature.
You know, there's a reason for that, and it's simply a practical limit that you run into. With my torsion balance, the balance had a total of about 1.5 kilograms of mass hanging on it. And that had the torsion wire that I was using stressed to about 70% of its ultimate tensile strength. If I had tried to use the 44.6 kilograms of the large masses, I would have overstressed that wire 20 times its tensile limit. So that's the practical limitation. There's no other reason.
Absolutely, of course. It's going to have a different heat signature. Of course. It's going to retain heat within its structure.
Now see, we're going to have a problem with the idea of thermal equilibrium. So let's see if we can go through this very quickly. Let's imagine we've got a thermodynamic system that is isolated, indicated by that blue box I've drawn there on the screen. And there is air inside the box that is at a temperature we'll call T1, and then I have two masses in there. Mass M1 is a large mass, M2 is a smaller one. M1's temperature is T2, M2's temperature is T3. Now when we start, the temperature of mass 1 is exactly equal to the temperature of mass 2. So T2 equals T3, but they're both less than the temperature of the air, T1. By the laws of thermodynamics, heat will be transferred from the air, which is at a higher temperature, to both of those masses. And it will look like this over time. Initially, the temperature of the smaller mass will increase at a higher rate than the temperature of the larger mass. So for a time period, temperature T2 will be less than temperature T3. But eventually the system comes into thermal equilibrium, where all three of the temperatures are equal. The temperature of the air has decreased, but the temperature of both of the masses has increased. A lot of people get confused by this. They think their countertop is colder than the cabinet that the countertop is sitting on, because that's the way it feels to you. But that's not really true. The temperature of the countertop, if you measure it, is exactly the same temperature as the wooden cabinet it's sitting on. The countertop only feels colder because it is better at taking heat away from your hand. Now the bottom line is this: in a system like I just described, unless you are putting heat into the system somehow, eventually everything in that system will equalize at the same temperature. And that's the condition we call thermal equilibrium.
More than a smaller object.
Yeah.
That's the point. Like don't you think someone would have picked
it's your knee.
Oh, right, sorry. So I don't need this again, you know.
No, you don't need to. You don't need to read that comment.
Oh, okay. Yeah, sure.
Anyway, Blue Marble Science jumps in.
Oh, Blue Marble Science, yeah.
Can you get the mouse and get up OBS? Because I'm thinking that the
what's that?
Get up OBS.
That's
no, it's fine. Yeah,
that's fine. One thing.
Blue Marble jumps in.
We need to get Cavendish's paper up as well.
Well, it's on the. Well, go on then. It's on the bookmark, isn't it?
Is it?
While these guys are fumbling around looking for references or whatever, let me explain what all the hubbub is about. This is a Cavendish torsion balance. It's very, very simple. We take a couple of small masses and we suspend them from a torsion element like a wire. And then when we move two larger masses close to the small ones, the masses attract each other. That causes the torsion bar to twist. That develops a torque in the wire, and we can measure the amount of torque and determine the force of attraction. It's just that simple. But Cavendish noticed something funny happening at times. Not all the time, but occasionally something strange would occur. And it went like this. There you see the case around the torsion balance. That's that blue line. And you see the small masses, that would be the yellow ball there in the center. And Cavendish found out that when he moved the large mass, the big blue ball, close to the case, initially the torsion balance would deflect just like it should. But over a period of time, if he watched it, the balance would begin to move a little bit more. And he wondered what was up with that, and so he did a lot of tests to try to rule out things like magnetism, and he found that magnetism was not having any effect on it. So he started wondering about thermal effects over time. So what he did was intentionally heat up the ball and move that into close proximity to the case, like always. And sure enough, initially, he could see the balance move to a new position, just as it should. But now, over time, the side of the case close to that large mass itself would heat up. Now that heats the air up inside the case, and you get rising warm air, which forces a descending column of air on the opposite side. And that pushes the balance a little closer to the large mass, as you see depicted here. Cavendish confirmed this thermal effect by cooling down the large masses. And now when he put a cooler large mass next to the cabinet, the initial balance movement was just as predicted, but again over time, this time, the side of the case close to the large mass would cool off. That causes a descending column of air on that side and a rising column on the other side, and that has the effect of pushing the torsion balance the opposite direction. So what do you do about that? Well, a couple of things. First of all, as long as everything is in thermal equilibrium, that is, as long as the large mass is at the same temperature as the case and the small mass, we don't have any issues. But another thing that you can do is simply take the measurements as quickly as you can after you move those large masses into position. That's what Cavendish did. It takes time for that cabinet to change temperature. Wood is not that great a thermal conductor. I addressed this issue in two ways. First of all, I ensured that everything was in thermal equilibrium. The experiment was in an environment that never varied more than about a 0.5 degree centigrade. Secondly, just as Cavendish suggested, I took all the measurements as soon as I could following movement of those large masses. Peter and Pete have tried to make a big deal out of this. There's no big deal. There's nothing to see here. It's all been taken care of.
We're going to get it up.
I don't think so.
Blue Marble jumps in on the conversation.
Oh.
Yeah, James Smith gave you the link.
Oh, did he?
Calculating the density of the Earth.
Yeah, that'll do.
Yeah, there you go.
Not that
experiment.
one. That one.
There you go.
Yeah, it's this one here.
Experiments to determine the
it
density
wasn't
of
this
the
one.
Earth.
Oh, you
Philosophical. If you accept. View PDF. There you go. Preparing publication. Have a drink of coffee in the meantime while you're
Absolutely.
there it is. This is the original paper. But anyway.
Absolutely, of course. But let's get back.
Going back to the comment. It's very important. Blue Marble Science jumps in on the conversation. He says perhaps you need to reread
the paper.
The paper. Heat differential didn't cause the movement. As Cavendish clearly states, unevenly heating the case will result in circulating air currents inside the case. Those circulating air currents can cause movement in the balance. So blue marble science is accepting that circulating air currents that are produced as a cause of heat,
as a result
differential,
as a result of heat,
can cause movement in the balance. You're misrepresenting his contention and what can actually happen. But then again, this might be a bit too advanced for you guys.
I like it how these globy people think they're brainier.
Well, I know that objects thrown upwards don't accelerate upwards, and I know that objects don't assume whatever temperature they feel like just based on their size. You really only need the IQ of a claw hammer to know those things, but you two guys didn't seem to get it.
Yeah, I know. Yeah.
Then you,
Yeah, I know,
and yet
yeah,
they've got fuck all to.
But anyway, so
Anyway.
we asked him about where does it mention about air currents in Cavendish's paper, and he replies back to his, but page 497.
Page 497.
Here we go.
Yeah, his discussion goes on at page.
Well, actually, I referred you to page 491, which you conveniently skipped. This describes exactly what I just went through discussing. Let me quote from the last paragraph. The next thing which suggested itself to me was that possibly the effect might be owing to a difference of temperature between the weights in the case. For it is evident that if the weights were much warmer than the case, they would warm that side which was next to them and produce a current of air which would make the balls approach nearer to the weights. That's exactly what I just said.
You get less temperature, you cool things down, you'll get less motion.
And Cavendish even warmed the room overnight
Oh no, yeah, sure.
to heat the air, but he still noticed the same effect.
Sure.
Because if you're heating the air, you're heating the objects.
Absolutely, of course, yeah. I mean,
And a small ball is going to be warmer
than
than a larger ball.
Absolutely, of course, yeah.
This is an effect that can only be observed when the system is not in thermal equilibrium. The small mass temperature has nothing to do with the effect. It only happens when the large mass is warmer or cooler than the case itself. That's when we can generate circulating air currents that cause the balance to move. As long as the system is in thermal equilibrium, this effect is not observed. And in fact, I never saw it in my testing. But then again, my system always stayed in thermal equilibrium.
Because they just want their gravity. They're not interested in heat. No, that can't be it. We're just going to ignore that.
Yeah.
You know, we're not going to design our experiment to take into account heat, to show to everyone that we've eliminated it
Yeah, I know.
from our experiment.
Yeah, they're literally brain dead, aren't they?
They're fucked up in the head.
Yeah.
You know,
Let me
they're
look at
literally
Blue
fucked up.
Marble's reply 5 hours ago. Look, you really don't get it, do you? He describes the problem in the very first paragraph I gave. For it is evident that if the weights were much warmer than the case, they would warm that side which was next to them and produce a current of air which would make the balls approach nearer to the weights. It's air currents in the enclosure if you heat only one side and not the other, not the heat, the air currents. But the heat creates the air currents.
Absolutely. And you're carrying out your demonstration in air.
Air, yeah.
Now you're changing your story. Early on, you claimed that heat differential alone causes objects to be attracted to one another. Let me play that clip for you.
So on one hand, there's a heat differential, causes objects to laterally move towards each other. Or there's this insane idea that gravity is the cause.
Again, heat, the transfer of thermal energy, is not a force, nor is temperature. We could produce the effect that Cavendish witnessed the same way Cavendish did, by unevenly heating the case that contains the torsion balance. And that would produce an air current that would cause a displacement of the torsion balance. But that's easy to control. All you have to do is simply keep the system in thermal equilibrium. That's what I did. But you mentioned another interesting fact, and that is that I did it in air, not in a vacuum. My objective was never to try to improve on the measurement of the value of G, I simply wanted to know if I could duplicate the results that Cavendish obtained. Nothing more than that. For more accurate measurements, this experiment has been done in a vacuum many, many times. The earliest one that I'm familiar with is this one. It's from the National Bureau of Standards, and they did this first in 1930 and then repeated it in 1942. This is their report from 1942. And on page 22, I quote, "The vacuum used in the pendulum case was always less than 0.5 millimeter of mercury. Experiments were made with a molecular pump giving a much lower pressure, but it was found at pressures below 0.5 millimeter, the damping factor of the pendulum became constant, indicating that at such pressures, the air resistance was negligible compared to the internal friction of the filament." That means the torsion wire. I wonder how my results compare to these results. Let's see. In 1942, they obtained a value for the gravitational constant of 6.673 plus or minus 0.003 times 10 to the minus 8th centimeters cubed, gram to the minus 1, and that should be seconds to the minus 2. There's a typo there. Look at the next line down. My results were these. I measured an average value of 6.632 times 10 to the minus 11th, but my dimensions are different. My dimensions are in terms of kilograms and meters. That's a more classic way of stating the gravitational constant. How different is that? 6.673 divided by 6.632 is a difference of 0.62%. I don't think I had a temperature problem.
These guys are,
They got mental health problems.
they're fucked up. They're totally fucked up. If they can't see the flaws in their own experiment, their
He literally
experimental
says that as
design.
long as the weights in the
You know.
case are at the same temperature, there is no change in the balance.
But how are they going to check
Change-
the weights are the same,
Same
temperature
temperature.
when they're of different masses?
Yeah.
This is how I measured the temperature of the case, the weights, and the ambient air. And you know what? Every time I did that, all three temperatures were exactly the same. Well, I think that'll just about do it. Thanks for watching. Hope you guys enjoyed it. Don't forget to tickle all those little buttons down there. There's a link to the Patreon and the PayPal. I'll have that in the description as well. And I guess I'll see you guys on the next one.